Would somebody please type in the chat pod that my voice? There we go. Okay. Thank you so much. We are going to get started right at 11. So in the next 30 seconds, I guess. We have one of the United States' best compressed air technicians in the room, Mr. Rodriguez. Wow. So incredible. Now that Edwin's in the room, I can't say anything that's even partially wrong because I'll get called out by the Brotherhood of Technicians. All right, so it is 11 a.m. Eastern. So out of respect for the people that got here, we are going to get started immediately. My name is Josh with Industrial Compressor Solutions, and this is a free webinar being put on by Compressed Air Towards Zero, and we are going to be discussing the efficiency of demand-side optimization, specifically trying to answer the question, where are my savings? So a couple notes from the one we did at 5 a.m. this morning. First of all, we found that this concept is way too big for one webinar. We felt like towards the end of the webinar this morning, it was definitely kind of getting dry and stale. So I want to concentrate on the first example. We make sure we go through it well, and then we will use the time available as we see fit. But I am going to plan on switching to questions and answers at exactly 11:40. So that being said, if you type in a question, if you have a question, you can type it in, and when we switch to the question and answer period, it will pull up on the screen, and we'll be able to talk about it from there. So again, my name is Josh with ICS. This is being put on by Compressed Air Towards Zero, and I have been directly helped on this immensely by Airlick in Slovenia, as well as 7 Bar out of Poland. So I do want to say thank you to those two organizations. This would not be happening without them. So a quick story. We went to a facility that had 225 horsepower compressors. They had a high percentage of leaks, and the customer was using one compressor fully loaded. And when we came in that day, the second compressor was turned off, which is not the normal, but it was turned off at that time. The customer wanted to find all the leaks. And when we did the leak survey, we found out that 71% of that first compressor was dedicated completely to leaks. And the question I have for you is, how much is it worth for that customer to fix those leaks? We're going to talk about that today. So again, my name is Josh. I've got about 25 years in the industry. I've spent most of my life as on the technical side, whether it be as a service technician or actually on the demand side, doing piping, installations, and work. I am a Navy veteran as well as a Marine. I own Industrial Compressor Solutions in Hampton, USA, and I'm very proud to be associated with Compressed Air Towards Zero, KGI, ISO, the AICD, and the Palmetto chapter of the Project Management Institute. So where are my savings? So let's start off by saying, what are savings? Let's try to get on the same page with an understanding that I am not an accountant, but I just want to give a basic representation of some of the different terms and cares that we hear when we're talking to our customers. Oops. So, cost savings versus cost avoidance. If we have an existing expense, for example, power for the air compressors, and we want to reduce that expense, that is an example of cost savings. Now, if we have to pay something to make this reduction, then we would utilize a return on investment for those cost savings against the total cost of ownership. Conversely, if we are trying to avoid a future cost, then that is a cost avoidance model. So, for example, a customer might opt for an extended warranty from the manufacturer or service company that's servicing their equipment. And their expectation is that by taking that extended warranty, they are preventing themselves from having to pay the future cost of an air end rebuild or a motor rebuild. So those are very distinctly different. The return on investment is relatively understandable, and the total cost of ownership can either be on the equipment level or the system level, but it represents every single cost associated with the life cycle of that equipment or system. So, total cost of ownership, return on investment, and then cost savings and cost avoidance are going to help us get through these through this webinar today. Now, I am going to be making a case today on a couple different items, and realistically, I should have started this. I should have started this a couple minutes ago this way and said, my hopes for this webinar is not to convince any of you of anything whatsoever. In fact, I will hope that you think I am completely wrong on everything that I say. I hope that not only do you think I'm completely wrong, but I challenge you to check me. I challenge you to take anything you hear that might not sound right or might not fall in line with your experience, and I challenge you to weigh it out, test it, and God knows, let's circle around and talk about it together. That'd be awesome. So, as I get back into this, my contention is that there is an efficiency of any type of optimization that we do in a compressed air system. And if we don't account for that efficiency of optimization, then we end up being in a situation where we are overpromising the customer, and the customer has false expectations. So this is a very, very bad concept for all of us. So hopefully we're going to be talking about some ways that we can make sure we don't overpromise our customers and set them up for the best possible success. So here's a super basic, super basic slide that's basically illustrating that as a function of time, compressed air system cost is going up. That is going up in artificial demand, it's going up in waste, it's going up in leaks, it's going up for a plethora of reasons. Sadly, not many of them are increase in production. So when we make an improvement, we are trying to optimize that cost. We're trying to reduce that cost and set us on a new path forward. I am going to be talking to you about the efficiency of these optimizations, but we're also going to be talking about the decay of optimizations. Just because we fix leaks in a system does not prevent us from having future leaks. So the rate at which that leak load returns to the size it was when we first did the leak study, that also is important for determining what we save and or what we don't save. hopefully, when we know what to look for, we're going to be able to work with our customers using benchmarks and thresholds to say, hey, we know that this optimization is going to start to fall off. Once we cross this line, now we say, okay, let's come back in and push it back down. When we talk about demand side optimizations, I like to compare it to holding a balloon underwater. It's not necessarily difficult to put the balloon underwater, but in order for this to work long term, we have to hold it there continuously. And therein lies the problem. The compressed air system would like to take a life on its own, and it would like to just consistently evacuate compressed air to atmospheric pressure, right? So we are holding it at pressure, and we are dealing with a very simple process. So a couple reasons why the savings that we're expecting aren't what we thought they were. Let's say that the compressor room is less efficient at the new demand profile. If we make reductions and optimizations to the demand profile, but our compressed air station or compressor room cannot efficiently supply the system at that new demand profile, we're going to have issues. If we're running two compressors in a cascading pressure band, well, if we're running in that second compressor, our pressure is lower because we're operating in that below the pressure set points of the first compressor. When we shut off compressor number 2, pressure comes up, and now all artificial demand leaks and waste is being overpressurized depending on our pressure control. If we make pressure reductions, we also decrease the amount of storage in our receiver tanks. So more intermittent demand is now having to be covered directly by the compressors instead of in the receivers. Now, if our unloaded power is too high, if our part load efficiency isn't good enough, then when we lose storage, when we change that demand profile, that reactivity back to the compressors, it's not even just power. You can adjust how many cycles of your inlet valves, solenoid valves. Technicians can be changing out solenoid valves and inlet valves, and depending on who's watching the system, it might be believed that that's an equipment level problem when it's actually a system level problem. If we try to use receiver tanks to cover intermittent demand, but we have to increase the pressure of the system to do it, to give us a differential pressure across the receivers to make them successful, well, now we're sacrificing the entirety of the system efficiency just for that one process, the attempt at process optimization. And then not only that, but there's a cost of the change in technology. So anytime we change technologies, for example, maybe we take like an air amplifier. Yes, we can provide X amount of CFM to a process, but at the same time, we have a separate source of compressed air that does the work in that amplifier. So that has to be accounted for in the efficiencies of the savings. And when we talk about decay, we can make optimizations in a plant and they're just adjusted back. Somebody doesn't like them. There's a couple mentalities when it comes to system optimization or demand side optimization. Sometimes we say, hey, let's remove the old way of doing things, right? Remove the old compressor, remove the old piping, remove the old way and build in the new way. The risk there is that if something doesn't work, breaks, or you didn't account for it properly, you can't put the system back the way it was. Well, the other approach is to leave the old method in place and then just valve it out, lock it out, whatever. Now, in that case, though, now you're in a situation where somebody could, on purpose or on accident, revert that system to the way it was operating before and cost you all of your savings. The third thing that can affect the decay is changes in employees and or changes in service companies. If the team overall, and that be the system person, the customer, as well as the service company, if those entities aren't aligned in the best interest of the facility, then those disagreements are going to result in changes to the system and a decay of the optimization. System modified is funky to me. It happens all the time, and God knows, heck, I wish the fact of the matter is I've done all of these things personally. I hate to say, but the system modifying, how many times have we serviced a piece of equipment? Have we aligned a compressed air system one way or another? And then we didn't return the valve lineup completely to the way it was beforehand. If you leave a bypass open, if something simple, and next thing you know, you have completely eradicated any optimization that you've done. And then what happens if the plant needs change? Whether that's an increase in flow or pressure or a decrease, both of those things impact the efficiency of your optimizations. So we're going to talk about leaks and leak load reduction, pressure reduction and pressure control, adding storage, compressed air to other methods, and then also piping optimizations. And like I said, at 11:40, I am going to stop talking and just answer questions. So if we don't get through to the end of this, I will provide it to anybody that asks the full presentation, as well as open myself up for questions and comments after the fact. So first of all, let's talk about leaks and leak load reduction. In order to get too far into this, I'm just going to flash this compressor control comparison chart. We've all seen this over the years, but effectively what we're looking at is based on the individual type of compressor controls, part load inefficiency is different. So if we're operating at 100% of the compressor, our expectation is that we're 100% power, 100% flow. But as we come off of that 100% flow, we do not have a linear reduction in power. And that varies by different types of compressor control. And I'm just putting that out there for a reminder moving into this. Now, in the scenario that we talked about, we had two 25 horsepower compressors in a facility where it was designed to have one of them running. It was designed to have one of them running and one of them on backup. Now, when we got there that day, the second compressor was off, but that was not the normal. Now, an interesting thing is about this, though, is because and I'm going to actually go one more here. So the system was capable to 236 CFM, but it was reliable to 109. And what I mean by that is the moment the second compressor comes on, our customer's reliability position has changed. As long as we have only one compressor running, if something happens to that compressor, the second compressor will come on and the plant still runs. But when we are operating in that second compressor, losing one compressor shuts down the system and causes pressure issues. So we're load unload compressors. So we said basically about the top 10% of the compressor is mostly efficient, but once we get out of that, we're not doing well. So I found it very interesting, though, when we look at these two control graphs on top of each other, this is representative of what it looks like when you have two load unload oil flooded rotary screws in a cascading pressure band local control. So what's really funky about that is at 109 CFM, we operate in two potential positions at the same time. We could be operating with compressor number one fully loaded and the second compressor off, or we could be running in compressor number one fully loaded and compressor number two running unloaded. Now, this is a completely different amount of power cost, but zero difference in flow supplied to the facility. Now, here's what else I thought was really interesting here. This is another case of the difference between pressure-driven and flow-driven. So in a system where the pressure is being held constant, then the compressor or compressors will load and unload to maintain that constant pressure or pressure band. Now, when the demand profile is higher than the supply's capabilities, what ends up happening is, first of all storage is used up, pressure starts dropping, and now the compressors are constantly loaded and pressure is changing based on changes in demand. So those two things can fight back and forth and completely change the way the compressors operate and everything from power to maintenance to whatever else. So in this case, like we said, 71 CFM was the leak load. Now, if we just word on the street, if we thought that a linear reduction in power matched that leak repair, then we might say that $8,244.60 was the customer's annual savings. My argument to you is that that is just not true. There are factors that affect the ability of that to be true. And realistically, the real number was closer to $2,938.51. So, like we said, if we look at, and I'm going to use the pointer. Yeah, okay. I'm going to use the pointer now. If we are operating at 109 CFM here, and we reduce 71 CFM, we do not go directly towards zero. This is not proportional. The inefficiency here is that we follow this line. So a change of 65%, a change of 71 CFM is only at best $2,938.51. It is not 8,000. That would be shown as having a line like this. Now, that 2,900 though, is that real? There's a question as well. First of all, are you going to fix every one of those leaks? If you do fix those leaks, how many seconds is that plant going to operate without any leaks? Now, I'm not saying that your leaks are going to break or the leak repair is going to break, but how long is that system going to operate before something else starts leaking? So we have the how much can we repair, as well as how long does it deplete that optimization. So, and I know this is a little small, I apologize, but there is a time value to the leak repair. Let's assume just for a second that we can fix 100% of the leaks, which in my experience isn't a thing, but let's say we can. That $2,938.51 is based on their operating conditions, their costs, as well as a full year of no leaks. Now, if we could assume, and it's a little oversimplified, I'm sure, but for the purpose of training, if we could assume a linear decay of optimization, then we would say in order to be able to save $2,900, it would have to take 2 years for that savings to decay back to the original point that we found it when we did the leak study. Now, if If it only lasted a couple months, we'd only save a couple $100. So this is an example. This is an example of something that we need to talk to our customers about. We need to gain an understanding of how long we have until that leak load is returned to pre-optimization. So we talked about cost savings, but here we have a scenario, like we said, where at 109 CFM, we could be just fully loaded on the one compressor, or we could be fully loaded on one and unloaded on the other. But that unloaded power cost would contribute to another $6,300 a year just running that second compressor unloaded. So maybe we need to look at both. What is the savings potential and what is the avoidance potential? There are efficiencies to both of these. If we look at the efficiency of savings, we're going to look at the percent of leaks fixed. We're going to look at the cost of the leak study. We're going to look at the rate of the optimization decay. We're going to look at the cost of repair. On the cost avoidance side, we've got to say, is the demand profile so even that it just sits there at 0% or and runs the whole time in an unload, or does it have a couple hours a week where it's running unloaded, or a couple points only? Where do we get to the point where that second compressor is running, depending on the demand profile of the system, that could be operating at 0 to 10% or 0 to 20% by the time it got to that point. So even that 6,300, just because the compressor turns on once, your customer doesn't automatically get charged that $6,300, right? So there's even an efficiency of the avoidance number as well. So as it pertains to leaks specifically, what do we save? What is the cost to repair? What is the time to deplete savings? And when does it make sense? Where does this threshold make sense to make sure that we're re-optimizing and holding that system where we want it to be? Now, partly I joke, and I should be careful with this because, being funny doesn't stop you from getting canceled, right? But I'm definitely not talking bad about people that sell compressors for a living. It's a great job. I've done it. And if there are plenty of scenarios where the customer calls you and says, hey, we don't have enough compressors to maintain system pressure, we need more air. And if you audit the supply side, you will see that you'll have pressure fluctuations. You'll see that your demand side is higher than your supply side. And depending on what they allow you to do inside their facility, you might not have any other way to go than to just sell another compressor. So please understand that I am not trying to be disrespectful to anybody, especially for doing their job. Now, that being said, if the customers will allow us to go into the plant, to walk the facility and evaluate wastes and inefficiencies, then there is a lot of room. There's a lot of room to make optimizations that don't require capital expense. My argument here, based on where to set the threshold, if we said that our cost avoidance model, we said, hey, we don't want to change our reliability position, right? So in the moment that second compressor comes on, immediately our reliability position changes. So if I say, hey, instead of calling me or calling a technician because plant pressure is low and you're scrapping, or you have a material scrap, or your scheduling production or whatever it is. Instead of calling us there, instead of that being your alarm line, let's push that alarm line down to before where the backup compressor comes on. Now, if we do that, then my question to you all is, how close to that threshold line are we, and how important is that number? In a small system like the one we saw with 109 CFM, how much of the time are we spending within 10%? How much time do we have before the system expands where that second compressor comes on? So it does make sense to consider permanent monitoring and measuring that flow rate against the threshold of where that second compressor comes on at. So I am going to push through this because this is recapping. And we're going to talk about pressure reduction and pressure control. Maybe, if I can hit the button. So we looked at a system that had 5 different types of processes. The sum of those processes was about 1,250 CFM. The plant operating pressure was 145, and they were running little over 200 kilowatts. When we looked at the pressure requirements of those different process groups, we found that they were all over the board. We found specifically that due to 2 of the types of processes, the entire plant was being held at 145 PSI. When we looked into it a little bit further, we found that those were not correct whatsoever. In fact, the reason that they were being held to 145 PSI was legitimate from the manufacturer, that the actual process did require 145 PSI. But what the manuals didn't say is that internal to the 6 or 8 processes that required that pressure was a regulator down to 72.5 PSI, and that then went to a pneumatic amplifier to 145. So the entire time, the customer was pressurizing their entire facility to 145 PSI and buying 145 PSI rated compressors when they just didn't need it. When we figured that out, we were able to take that facility from an annual operating cost of about $192,000 in power down to 55. Now, there were some other optimizations that we'll discuss a little bit later here, but I have to be really, really honest with you guys and say that this is an example where the plant manager changed and they undid the valves. They immediately went back to running 4 compressors. In fact, the last I know, they purchased 2 additional compressors, and now they're running all 6 compressors with no demand change from when I had it set at 2 compressors. So even when we think we win, sometimes we don't win. Here's another scenario when we talk about pressure reduction. In between these points 1 and 2, between 1 and 2, there's a difference of 359 CFM, but only a difference in 3 kilowatts. And when you consider working in a facility where you save the customer 359 CFM, and they're expecting that to be, 55 kilowatts of savings, and you come back and say, oh my goodness, it's 3 kilowatts in savings. That's that's like 5%. That's 5% of expectation. That's a pretty rough scenario. So when we look at pressure reduction, we talk about pressure reduction in 4 key places. And when we look at our compressor set points, and I'll use the arrow thing, we control pressure at the compressors, we control pressure at the plant, we can control pressure at zones or process groups, And then we can also control pressure to the individual processes. It's an important thing to understand that pressure mapping and flow mapping of the entire system is going to be critical to know when and where to put the pressure regulation devices. There's a question of having one set of pressure control devices, or do you have a second for a backup? Are you adjusting those pressures incrementally? What is the relationship of the different pressures and flows? That's how you're going to put that map together and figure out where to reduce, how, and how much. We talked about this a little bit earlier in that first scenario, but it's also the same in the second scenario. This is what we're talking about, where if the demand profile is underneath the supply capabilities, then pressure will be controlled either to one specific set point or a pressure band, and the compressors will load unload to maintain that constant pressure or pressure band. Now, in that case, the efficiency of the supply side anyway is highly dependent on the part load efficiency of the compressors, the equipment in the compressor rooms. The reliability position varies based on what you have for backup. Now, like we said, when the demand profile exceeds the capabilities of the supply, then the supply will stay. First of all, the capacitance will drop, pressure will reduce, and now you're operating below your unload set point. So all compressors are running fully loaded, and plant pressure is varying up and down as the load changes. Now, in this case, the funny thing is that system specific power actually looks better at the reduced pressures because the air compressors take less power to run at lower pressures. Now, that being said, though, that's all fun and games until you go below the pressure set point that starts causing problems in your facility. When you start having scrap, when you start having to schedule production, you're no longer winning because you've got a good specific power number. We're going to skip over this. We got 4 more minutes before we go into questions. Adding storage. There are 6 common uses for receiver tanks in compressed air systems. In the compressor room on the wet, so before dryers, we have pressure balancing as well as water removal. After the dryers and filters, we have intermediate storage, which stores air for intermittent demand and also aids along with the pressure balancing for compressor control operation. On the distribution, if we have pressure drop in a long run of pipe, we can use a receiver tank on the distal side of the piping to eliminate some of that differential pressure. And then on the process and process groups, we can use storage for process protection. So like if we have either critical pressure or we have a high scrap rate, if there's small fluctuations, we can put a storage volume there with the check valve and or amplifier to make sure that we don't go below. And then we also have event storage for intermittent demand on the process level. But we look at some of the things that can cost us our savings here. If the demand's above system capabilities and it's trying to take storage from before the dryers, now we've no longer limited the airflow through the dryer based on the compressor capacities. Now we have the compressor capacities plus the capacitance of the tank before the dryers, and all of that can rip through the dryer, causing variations in pressure dew point. God forbid we don't have properly sized, properly functioning drain traps. I would assume that every single person in this group right now has been in a situation where they're standing in front of a receiver tank, but the system does not look like there's a receiver tank. And that's because it's full of water. There is no storage. Intermediate storage, if we lose pressure control, then we lose differential pressure across the receiver and we lose all intermittent demand or effective capacitance. If the demand profile changes, receiver loses effectiveness on the distal side of a pipe that's too small, especially where we change the demand profile on that same line. And that could be as simple as increasing artificial demand or increasing cycle times, waste, leaks, all of it. Process protection. If a check valve fails, that one small little check valve took away the protection to that process and now has the entirety of the compressed air system back trying to feed it. Similar, if the demand profile changes and supply pressure is reduced, where we are storing for intermittent demand, our capacitance goes away as that differential pressure is reduced across those receiver tanks. It is 11:40. So I do want to stop there. I'm going to point out my little high chair here and talk about when the demand profile gets lower than what the compressors can handle. If you see this little chair looking here, that back of the chair is the only time that compressor was loaded. This is the unloaded time, and then this is the shutdown period after it. So when we get below the capabilities of the system, now the compressed air system is too big to operate correctly. We're going to have high wear and tear on the equipment. We really need, in a case like this, we need to temporarily put in smaller compressors until the system gets up and operates the way it's supposed to be. So that being said, I'm 1 minute late, but may we please look towards the questions. Oops. Let's see. I might need help getting the questions up. Let's see. Here it is. So the first question is from Mr. Edwin. Edwin is a master technician, the gentleman I was talking to a little bit earlier. He says, what you're talking about is so important in our industry in terms of efficiency. Feel that issues experienced with their equipment and overall operation related to the compressed air system needs to be addressed in a multi-pronged approach. And it starts at the technician level and the salesman level, where the disconnect of knowledge is usually located. Edwin, I think that's a really great point. I do think to some extent, in the old days, I used to say that there was a brick wall between the service guys and the sales guys. And every day bricks are getting added to that wall, and it's all of our responsibility to daily be removing the bricks from that wall. But it's the best interests of those two professions don't always align with each other. But hopefully, with good communication, training, teamwork, and a relationship with a customer, both are part of the critical team that leads to that customer's success. So thank you very much for that statement. Let's see. Okay. System optimization and equipment optimization should be synced together when it comes to optimized operation, but the problem lies with lack of training and customers' attitudes in maintaining their equipment whenever we're not present to address the issue. Many factors, as you mentioned, impact the overall efficiency. Man, this is a great point. I think that sometimes, I guess for me personally, right, like if I've in the past gone and troubleshot a compressor and I said, hey, this solenoid valve is bad, or this inlet valve is bad, if the compressor doesn't have a history of it, there are things that I can check. Like I can check load cycles. Well, on newer compressors. In the old days, we couldn't really do that. But on the new microprocessors, we can check how often it's loading and unloading. We can see how many times the inlet valve's opening. So we can see load and unloaded hours. So we can kind of get a feel if it's been operating correctly or not. But I think the more times that one specific type of component fails, it's easier and easier to say, hey, maybe we should be looking at the system approach. Um, just because the oil cooler is dirty doesn't mean that the whole world's falling, right? It could just be that it got dirty, right? So, yeah, I think I'm with you on this, Edwin. I think that's a great point, and it's something that we all have to strive and work for. That's for sure. All right. Figuring out how to optimize a customer's equipment versus power cost savings is always tricky because it doesn't last forever. And the last thing we want to do is run any compressor. Oh, yeah. Oh, yeah. So, our supply side experts, when you talk to some of the guys that are really good in compressor controls and supply side optimization, there's all kinds of products, services, and methodology for optimizing the supply side. But that being said, you're right. That is for a specific set of criteria. So if the demand profile walks above or below that set of criteria, then the efficiency and reliability of that supply side is gone. So yeah, very good point there. All right. Anthony Nicotera, does the plant have continuous monitoring of actual cost of electricity for those 6 compressors versus the 2 you had it set at? I can't believe the CFO actually wants to spend the difference in cost under waste category. Oh man. Oh man. I really wish this wasn't true. Because this is a scenario, a customer and an industry that I absolutely love. And in fact, when I did the audit down there, they didn't believe me that the piping changes and pressure reduction would do what I said it would do, because when I came down there, they had 4 compressors running and they were still having pressure problems. And I did my audit, and then I did all the math, and I said, it's going to cost you about 60, I think around $16,000 to make the piping changes to get this done. And the customer said no. And I told him, I said, how about this? I'll guarantee you that if I do these piping changes, 2 compressors will shut off. And if they don't, you don't have to pay me for the work. Well, so the customer said he would do it. Now, as a side note, there was one transducer that, instead of being on the appropriate piece of equipment, was on the other side of the plant and just assumed for that piece. So whenever I did first put the valve lineup into the new piping, it didn't work. But that's because the system thought it was at a different pressure than what it was. Horrible, but I ended up having to run a half-inch line 10 feet to get the pressure transducer tied into the right system. Now, as soon as I did that, though, 2 compressors down, off immediately. It did not last the week, Anthony. By the end of the next week, I think I left there on a Friday. By the end of that next Friday, they called me and said all 4 compressors are running and we're having pressure problems. The plant had on purpose changed the valve lineup back to the other operating place. And yes, sir, they are running 6 compressors right now. And that is what it is. It is a great failure on my part. That customer, and I'm still friends with the corporate level there. But that was a great lesson to me about the lack of importance sometimes in right versus wrong. Sometimes the customer has a way that they want to operate, and if you don't have buy-in, it doesn't matter what your way is. you have to have buy-in from everybody in the facility. And to some extent or multiple extents, I failed at that. So that's it's definitely a it's definitely a scenario that stings, but it's also taught me a lot over the years. So um, let's see. Does anybody else have any questions? Well, I would like to thank you all. I would like to thank you all for coming. I really appreciate it. If you have future questions or comments, please reach out to me on LinkedIn, reach out to me on WhatsApp, and let's talk about it a little bit. Um, don't trust me on anything. Explore for yourself, learn it for yourself. Um, and I can't wait to talk to you all about this in the future. Thank you very, very much for coming out today. So, thank you. All right, we got another question here, real quick. Edwin's talking about thoughts on running four 50 horsepower Solaires with spiral valves, um, and all are modulating together. Oh, God. Okay. God, I love this question. Edwin, you are so awesome, man. All right. So, in the top 50%, and the top 50% of a Conotrol power sync spiral valve, um, or turn valve, on the top 50%, they're halfway decently efficient. So if we talk about 450 horsepower compressors, effectively what we're doing is making one 200 horsepower compressor. So as long as the demand profile lives constantly between 100 and 200 horsepower, then we're pretty squared away. The downside is if at any time the demand profile goes below 100 horsepower, you have multiplied your inefficiencies by 4. So now you have 4 compressors operating inefficiently below where they're supposed to, and it can be a pretty big issue. I would be taking a relatively hard look at the demand profile, including storage. But yeah, we would, in that case, I would say that compressed air system needs to be held at above 100 horsepower, and or use a type of some sort of automation to make sure it stays in the proper position and it's not hurting the compressors. So, and that being said as well, God knows passing oil and water because it's not operating at the right in the right way. So, thank you for that question. Let's see. Yep. Okay. All right. Anybody else? Well, thank you again, everybody. Have a great day, and you guys be safe out there.